simplifying exponent rules and simplifying radicals, part 2. So once we start getting to the next thing is, what is a radical? A radical expression is something that looks in this family right here. You'll have this symbol. Most of you recognize this as a square root symbol, but it's actually a radical. You are beyond the square root. The square root is only the very first radical. There is an infinite number of radicals in that family. So what really has to be here is this little n goes right here. And then you have some number inside. This n is called the index. This number underneath is called the radicand. And this whole thing right here with the n and the symbol, this is the radical symbol. So the index tells you what type of root it is. When there is no n, you don't see anything there, it's called a square root. So the n represents a 2. Okay, so you might want to write that down if you're unfamiliar with this. No n shown means n equals 2. Just like we don't write a 1 exponent on something, we don't write a 2 index on a radical. But any other index after that must be written. So we can write that over here. The square root looks like this. N is 2. That's the square root. Okay? All other indexes after that have to be used. Now, by definition, the nth root, this is called an nth root of a number. Nth roots are just fractional exponents. So radicals are just fractional exponents. So if you have a square root, that means it's that number to the 1/2 power. And because radicals are just fractional exponents, all the exponent rules apply. So I don't need to have a bunch of different rules for radicals to simplify them. I can just treat them as exponents and do all the exponent rules. But there is some ways that we can do simplifying radicals that are a little bit easier and quicker to do without having to switch everything to exponent rules. Here are some of the things that will make your life a little bit easier to understand and to use. First off, let's start with this. I have the nth root of something to a power. Well, since the nth root is literally a fractional exponent, this means this is a to the m, and then I can put that whole thing in parentheses because that's the radicand, and raise it to the 1/n power. So I can look at this as a exponent rule. A power raised to a power you multiply, and so then this becomes a to the m divided by n. So what does this mean to us? That means if I see a fractional exponent, the bottom number of that exponent is the radical. That's the index, always. The top number is the exponent that goes on the radicand inside. I can look at it this way too. What if I have the nth root of a number and raise that to a power in this fashion? So this is 1/n raised to the m, and you get exactly the same answer that way. Now I'm showing you this. A lot of times people say, well, this becomes that. But these are equals. They go both ways, which means if I see that, I can write it like that. It goes both directions. Okay? So all the rules apply. Here are some ways to look at this and to change back and forth if you need to. So the next thing is, how do I go about simplifying radicals? Well, I'm going to show you some of the problems here, but we can use exponent rules to simplify, and then I'll show you some other ways to do it also. But what does it mean to simplify a radical? What do I have to go through? Now, I'm not going to do all of these little things for simplification at this time. I will at a later date maybe show you some examples of some of these other ones. The two major ones here is number 1 and number 2 are the two most important ones for you to deal with. Number 1 is we need to remove all perfect factors from the radicand. And again, at this point, if it doesn't make sense, it will once I show you what I'm talking about. The second one that's very important is this. You can have no radicals in a denominator. And they have these conventions so that when people from around different parts of the who are working on math, they know how to express an answer. There's easy comparisons as we do it. So if everybody had different rules and ways to write what simplifying means, then you have a bunch of different answers and no one can compare answers. So they do, this is what you have to do, everybody does, so that we can make sure we all have the same outcome. The third one is I'm going to talk about, and we'll deal with it as we come across it. Combine sums and differences of radicals if possible. And so I'll express that one at a later date. Additional properties, things you want to do, want to know. And then I'll get into more details here. Additional property I need you to understand is this. The nth root of something to the n power. It is the absolute value of a if n is even. It is just a if n is odd. This is kind of important to remember, okay? Especially as you get more advanced mathematics. A lot of times, when you're dealing with square roots and stuff like that, it's not going to be an issue for you so much. It's only when it's really a variable, not necessarily a number, but numbers work also in this scenario, okay? And it boils down to this. For square roots, you cannot take a thing with square roots, but really for all even roots. You cannot take an even root of a negative number. So some numbers are not allowed. That doesn't mean I can't plug in negatives or anything like that, but when I get all said and done and I simplify what's underneath here, that number underneath here, the radicand, can, when n is even, that radicand cannot be a negative value. It doesn't exist. It's undefined for you at this point, okay? So that's why you need the absolute value aspect of it. Whereas for even odd roots, it doesn't matter because you can have a negative outcomes, all that kind of stuff with odd radicals, and you'll see as we move along. So it's just whatever the a is, that's what it is. Positive or negative, it doesn't matter. You'll notice in part 1 it says perfect factor in a radicand. Well, what are those things? Well, let's talk about those. We'll look at a couple of them, and you can expand the same concept. Perfect numbers, otherwise known as perfect squares for our purposes right now. This is used for square roots. Perfect squares are 1, 4, 9, 16, 25, 36. Hopefully you see a pattern emerging here. If you do not, this is 1 squared. is 2 squared. This is 3 squared, 4 squared, 5 squared, 6 squared, and so on. Hence the name perfect squares. They are squared values. With the exception of 1, we don't use 1 when we simplify radicals because 1 is a factor of every number, so we don't deal with that. We don't worry about that. These are the perfect squares, perfect factors that you're going to be looking for. For cubes, the same concept. 1 cubed, 2 cubed. Actually, you have negative values also. Actually, for cubes, I'll just do the negatives too. So I have plus or minus 1, plus or minus 2, 8, plus or minus 27, plus or minus 64, plus or minus 125, and so on. These are pretty much 1 cubed, plus or minus 2 cubed, 3 cubed. So you can see how you get your perfect values. Just take 1, 2, 3, 4, 5 and cube it. This is 4 cubed, minus 5 cubed, and so forth. And that can generate fourths, fifths, sixths, and so on. Okay? So you see for cubes, because it's an odd exponent, I can have positive and negatives. But for evens, like square roots, there's only the positive values. There's no negative values associated with it. So these things are what we're dealing with. And let's do a simple example of how I can simplify something. I'll show you what I'm talking about. Okay? I'll show it to you 2 different ways. Oops. So here's an example. I'm going to simplify the square root of 9x to the negative 6, y to the 4th. So like I said, there's several ways to do this. All right. One is I can look at this as all exponent stuff. If I look at it as an exponent stuff, hopefully you can see that there is the power rule in here. 9, you want to write as a power. 9 is a perfect square. Right? It was on our list. So I can rewrite this and just take a look at it as 3 squared. And then I have an x to the negative 6. I have a y to the 4. And because that is a radical square root, it is all raised to the power 1/2. So I can think that. By power rules, and this becomes 1/2 on each of those. So it's 3 squared to the 1/2. I'm really writing all the little tiny steps here. This is x to the negative 6 to the 1/2. This is y to the 4th to the 1/2. And then I can simplify that out. 2 times a half is 1. X to the negative 6 divided by 2 or times 1/2 is negative 3. 4 times 1/2 or half of 4 is 2. And you can see for these 3 base numbers, this is the only one that is negative. So by the negative exponent rule, 3 is on top, y squared is on top, x to the 3 is on the bottom. Because when you move it to the bottom, the sign changes to positive. It changes sign. And so that is the simplification of that through an exponent rule approach. There are other ways to do this also, but we will deal with those at a later date. Let me show you this one. What if I have let's do this one. 4x squared y squared and the cube root of that. I have something else there too, sorry. Times, and we'll do the cube root of 2x squared y. So how do I simplify that? Well, there are some other ways to look at radicals also. The major one is this. If I have, and it goes from the power rules. They're very similar to the power rules. Two different bases, then I can split a radical. Like so. And the same thing is if I have it in a fraction form. Again, if you look at the exponent rules, the power rules, the 3 and 1, you'll see the similarity of this from there. I can split it this way. So if I didn't want to change the exponent rules and I wanted to do this, I can do it in this fashion right here. So this is something you want to remember if you want to stay in radical form. They have to be the same radicals. As you can see, I have 2 of them that are being multiplied together that are the same. So I can merge these together and they become one radical. On top would be those 2 things. So 4 times 2, that's an 8. I have an x squared and an x squared. I'll just write it out. I don't want to confuse too many people. On the bottom, I'll have a y squared and a y. Cube, this is 8. Product rule, x to the 4th, y to the 3rd. And then you can break all these apart. Here they're all together. I can split it all apart. 8 is a perfect cube. That's why I want to split it out. I have the cube root of x to the 4th. I have the cube root of y to the 3rd. So you can see how things are going to work here. The cube root of 8 is a 2. The cube root of y to the 3rd power, that's that one rule, that just becomes y. And then this right here is interesting because I have 4 x's, right? X times x times x times x, right? Let me ask you a question. Can I write that in this fashion? Since there's 4 x's in there, can I just clump 3 of them together and leave 1 x like that? And the answer is yes, I can. Why did I want to do that? Because that is a perfect cube. It matches this index, which means it's going to do like this did. And I'll get, there's the 2. This part right here simply becomes x. And I'm left with 1 x underneath that radical. And that is the answer you're looking for. Again, a lot of practice has to go into this, but these are basically the rules. And so we're going to spend some time getting used to all these rules and practicing these rules and so forth and so on. And that ends that.